Hello, everyone. Well, I'm Eduardo. He's Héctor. We are not Jordi. Jordi is over there. We switched our talk, but mainly the topic is the same. We are going to talk about how the EIP4844 is going to affect rollups. And as most of you know, this is going to be the end game for transaction cost. So we are going to give kind of overview of what that means for secret rollups. I'm going to make a kind of a summary and put some numbers in the table. And later on, Héctor is going to explain how this affects to our rollup. So let's start by talking about some key points about the 4844. The first thing to know is that right now, currently, secret rollup are using cold data to publish transaction data or state diffs. And now we are going to switch to a new paradigm in which we are going to start to using blobs for publishing this data. So each blob, it has available 128 kilobytes of data. We are going to have 6 blobs per block. And one important thing, especially for node operators, is that the blob is going to be only available during 18 days. Mainly this is to not blow up the hard drive space of validators. And that means that probably we are going to see how archival blobs provider are start to happening, because if you want to have this data after this time, you need to ask to this provider for the data. An important thing to mention also is that we are going to move from 17 gas per byte to 3 gas, and mainly this is the main benefit of this. And another important thing to mention is the fee market. The fee that you are going to pay using blobs is different to the fee that is computed on the execution layer. Here we have a schema, basic schema how this looks like. We still have regular Ethereum transactions, as you can see here, but now we are going to have a new type of transactions, the data transaction that contains a blob. And these blobs can be verified on-chain due to the commitment. Héctor is going to provide more information about that. So yeah, the first thing to know when we talk about data cost of transaction is the prover. Usually people believe that the prover is a bottleneck in terms of cost, but I've been talking about this since last year. Prover is not the bottleneck anymore. You can repeat it with me. Prover is not the bottleneck. As you can see, the cost of a transaction is quite negligible. And this is some numbers of our current prover. It takes 2 minutes to make a proof of a batch. A batch is more or less 500 transactions. And we are going to add a lot of improvements on our proven system, like backups and other things that probably is a topic for another talk, not for today. But that is the key point, that the prover doesn't represent the most part of the cost of a transaction. So what are the costs of a transaction then? So we have 4 costs here. We have data availability, we have sequencing, we have prover, and we have aggregation. Data availability is paid for every byte posted on chain. Sequencing is when you publish the transaction on L1 and you need to pay this constant L1 transaction, but it's shared among all the batches that you are submitting to the network. Then the prover cost is constant hardware cost and is for each proof computed. And finally, we have the aggregation that is also constant, like the sequencing, and sharing among all the sequences aggregated. Don't get confused by this scale. We will see later on, but it's just kind of a glimpse that the data availability is the most important part on this cost. So this is our current numbers before going to the 4844. We are paying 16 byte cold data. And well, as we previously mentioned, we are going to use 128 kilobytes for sequencing these batches. Internally in the JKVM, we have the CK counters. Mainly this is what limits us to group transactions. And the thing is, with backups in the coming months, we are going to remove these counters. But at the end, it's just a way to make groups of transactions that are being able to be proven. Taking a look at this number, as you can see, for instance, 350 ETH transfers is around 39K bytes per batch. Well, you have that. You can see here that depending on the type of transaction, we need to submit more or less data on chain. And finally, you can see more or less how many transactions we can include in just one blob. So for instance, we can submit the data for 1,127 transactions in the case of 8 transfers, or around 350 in the case of Uniswaps. It's important to mention that obviously, well, the price of ETH for these estimations is, well, some time ago, but obviously the price of Ether has an impact on the price of the transaction on L2. So let's put real numbers here, right? This is what we are paying currently. Currently, we are paying the 95% of the cost of submitting transaction to L1 because of the data availability. If you take a look, sequencing is just a 4%, the prover is negligible, and also the aggregation. So this pie represents more or less where are the costs. And why this is so important? The thing is with the 444 and this Ethereum rollup-centric roadmap that we started in 2020, we are decreasing this around 7 times less. And that is why this is the end game for transaction costs for rollups. So, for instance, well, it's hard to see, but I will try to explain it. This is an screenshot of the blob scan. A website in which you can take a look to the blobs that are happening. This is, for instance, something in Sepolia. And here, even it's hard to see, but mainly we have, if I'm not wrong, 5 blobs. One is not in the screen. And the first thing that you can see here is the free market price. The thing is, if you include 3 blobs in a block, that means that the price is going to be constant. If we include more than that, the price of the gas price is going to increase, and if it's less than 3, the gas price is going to decrease. Now it's hard to know what is going to be the price. That depends on how many rollups are using blobs. But we expected at the beginning the price is going to be really, really low. Another important thing to see here is that if you take a look to the blob as called data gas, that is this thing, you can see that is 7 times less than if you use cold data. And that is why it's so important this for rollups. And now Héctor is going to give you more details about how this affects our system.
Hello. OK. Let's start with the funny part. So to be slightly more specific, a data blob, I like to see the data blob as a vector of field elements, each of which are over the BLS scalar field order. And the vision I like more is seeing these elements are being evaluations of a given polynomial under some sets of predefined values. In this particular case, is a set of roots of unity. But also, it's important to notice that from L1, we are not going to be able to access any elements in this vector. But the only thing we are going to be able to retrieve from any smart contract is through a new opcode, which is called Blob Hash. Okay? And it will basically give you the SHA-256 of the commitment of the polynomial that represents this vector. Okay? And only with this information we need to be able to prove that what we are proving off-chain in L2 is the same that what you can retrieve in L1. Okay? So the main issue here is that in L1 you are forced to play with what you have. In particular, you are forced to play with the KCC commitment over the BLS. But in L2, we do whatever we want. We do whatever it fits better for us. Okay? And in particular, we are not using the KCC commitment, but we are using our own proving system. So in some sense, we have to fix the inconsistency between what you have in L1 versus what we do in L2. Okay? And we will see that thanks to a new precompile that will be introduced in this EIP, we will be able to fix this inconsistency. Okay, and well, in particular, the trick is well known to fix this inconsistency, which is called proof of equivalence protocol. Okay, and basically the idea is to prove that what you have committed on-chain is the same as what you commit off-chain in L2. Okay, so basically a prover sends to a verifier the two commitments. Okay, then for sure this protocol will be non-interactive at the end, but just to, I think it's more intuitive seeing this interactive. Then the verifier will send unpredictable and random point. And then the prover, what it has to do is to prove that the evaluation of the polynomial of both committed polynomials under this point are the same in both cases. Okay, that's why he's sending back the evaluation and both proofs. Okay, and trying to be slightly more precise in how we are going to work with this EIP. So basically, the idea is that first, we are going to compute off-chain everything that we need for proving the correctness of the KCC commitment. Okay, so basically, we are going to be computing the random point as the linear Poseidon or the information inside the blob. Okay, this is all off-chain. And then we are going to compute the proof and the evaluation. Okay, and this is the information that we send on-chain. Okay, at least in the first part of this data flow. And basically, the smart contract, what we'll do in the first instance, when we sequence all the batches, is checking that this information is correct. Okay, so it's like a first guarantee that what is on-chain is what we like to prove in the next step. Okay, and in the next step is where we do all the work logged in the L2. Okay, so it's more or less the same, but basically, we are going to use our proving system to prove that Z, so the random point is well computed, meaning that is the linear Poseidon of the information inside the blob. And not only this, but also that the evaluation of the polynomial that represents the blob is precisely what we have verified in step 1. Okay? So basically, if in the next step when we prove that the batches are correct, we are able to verify this proof, that will mean that, well, not only that the evaluation is correct, but also that it coincides with what we got in the previous step. Okay, let's see now the proving architecture. Okay, so this is more or less the summary of the architecture that we have from the proving perspective. Okay, notice that, well, basically what we do is we prove the correctness of one batch of transactions, but not only one, but using aggregation, we're able to verify just by sending one transaction, just by sending one proof on-chain, that all the transactions inside all the batches are correct. Okay, and we basically aggregate all the proofs in what we call the aggregation stage. Okay, and this is what we have right now. But now, with the EIP4844, we will need to include the proof of the blob, okay, which is the proof of the correctness of the evaluation. And in particular, what we are gonna change from the previous architecture is we are gonna cut off after computing all the aggregations of all the proofs of all the batches. And in this point, we are gonna introduce the proof of the blob. Okay? We are gonna introduce the proof of the blob, which is the proof of the correctness of the polynomial evaluation, and we are gonna aggregate this proof with the output of the previous aggregation. Okay, this is what we call our inner blob prover. And then not only, we are not going to stay that, but we are going to also aggregate the proof from one blob of a set of batches to proofs of other blobs of other set of batches. Okay, so at the end, we are just going to send up one transaction to L1 proving the correctness of many blobs that points to many batches. Okay, and well, just going a little bit inside the details, these are going to be the public inputs that we are going to add to the inner blob prover. Okay, there are more of them, but just to mention a few relevance, we have the blob state root and the new state root, blob state root, sorry. And we also have the accumulated input hash, which is important because here, well, the accumulated input hash basically is, it's like what relates one blob to another one, like in a blockchain, okay, we are going to relate the previous blob with the next one. And in particular, here, we are going to be able to decide if we would like to go for the EIP4844 or not. Because, for example, let's say where we have a period where the blob cost is much expensive than the cold data price. So here we will be able to decide if we are going to keep putting things inside the blob, or we prefer to, for a short period, come back to the cold data solution. Okay, and in the inner blob we have all the public input related to the blob itself. But then here in the outer blob part, we have public input not only related to the blob, but also to the set of patches that you are approving. Okay, so here, for example, you can see that we again have the block accumulated input hash, but we also have the state root, the new one and the old one. Okay, it's basically the state changes that you encounter when you process all the transactions inside the blob. Okay, and well, in order to prove all this stuff, our solution was to create a processor that is able to interpret all the, let's say, state changes that are done due to the transactions inside the patch. Okay, so basically we have like a gigabrain, okay, which is what we call our JKVM processor, which is able, well, we design it like in a distributed manner, meaning that we are not encoding all the logic inside the same processor, but we are distributing them among different coprocessors. Okay, for example, we have a part that deals with arithmetic operations. We have another part which deals with binary operations, for example, well, let's say that what is able to do and what is not able to do this main processor is thanks to the ROM part of this processor. Okay, this was the old processor. But remember that I told before that the blob proof is in some sense independent to the batch proof. So we needed to create a new processor, which in principle it can be thought as a subset or as a subset of the original processor. So for example, in the left side, we had some specific machines or specific coprocessors to deal with padding operations and clean operations. And here, in the new processor, which will be much shorter than the original one, we will have just a subset of the coprocessors that we had in the original one. Okay, in particular, the arithmetic state machines will only need to deal with much less equations than the original one. Well, and finally, just to give you a glimpse of how we are doing these things, this is like the bunch of the computations that are encoded in the ROM of the new processor, okay? And in particular, as I have explained before, the main objective, at least for now, of this new processor is proving the evaluation of a polynomial. Okay, and here in the upper right side, we have the formula for computing this evaluation. And here we have the assembly code that is performing basically this evaluation. Okay, as you can see, it's the evaluation of a polynomial of degree 4096, which is the size of the blob.
Yeah, finally, I would like to explain a little our roadmap. This is not a commitment, it's just our intentions, just to make that clear. Well, as you can see, right now we are onboarding CDKs on the new aggregation layer. We can talk about that in the booth. We have promoting that a lot. We are working on the EIP4844 currently. And also, in parallel, we are working on the Erigon RPC that is going to happen very soon. And also, we are going to check our infrastructure to add Erigon as a new sequencer of our network, with the idea to increase the TPS of the JKVM, but also of the CDKs. We are also working in PIL2 and backups, variable degree composite polynomial, that are the things that I mentioned before in regard of improving prover performance. And we are developing the aggregation layer V2, aggregation layer V3, and especially also important and interesting for this talk is the data completion. We have saw that how easily we can decrease the cost of transactions by a factor of 3 or 7 or something like that. But we are also going to add data compression to the data that we are submitting to the blobs. And with that, we can achieve bigger factor compression and cheapest transactions. So yeah, mainly this. Thank you for coming. And if you have any question, you can find out around. Thank you.